All, welcome back. Today we'll be continuing with the chapter classification of elements and periodicity and properties, class 11 CBSE part 2. So, Dornier traits were proposed by the German chemist Johann Wolfgang Dornier. He attempted to classify elements with similar properties into groups of 3 elements each, called traits. The key idea behind these traits was that the atomic number of the element in the middle of the triad would be approximately equal to the average of the atomic masses of the other 2 elements. For instance, one of Dornier's traits consisted of lithium, sodium and potassium. The atomic masses of lithium is 6.94 and that of potassium is 39.10. Interestingly, the atomic mass of sodium, 22.99, falls nearly in the middle of the atomic masses of lithium and potassium. Not all elements known at the time could be classified into triads. Only 4 triads were identified by Dornier, leaving many elements unaccounted for that. Johann Newlands, an English scientist, made significant contributions to the early development of the periodic table in 1866. He arranged the 56 known elements in increasing order of atomic masses. Newlands observed a pattern where every 8th element exhibited properties similar to the first. This observation led to the formulation of Newlands' law of octets. The classification of elements based on octets was only successful up to calcium. The discovery of noble gases posed a challenge to Newlands' arrangement, as they do not fit into the periodic pattern without disrupting it completely. Dmitry Ivanovich Mendeleev, a Russian chemist, introduced his periodic table in 1869. He noticed that the properties of elements, both physical and chemical, repeated periodically with their atomic masses. Mendeleev's periodic law, also known as Mendeleev's law, states that the chemical properties of elements are a periodic function of their atomic weights. Advantages of Mendeleev's periodic table. It accommodated newly discovered elements without disturbing the table structure, including germanium, gallium, scandium. Mendeleev's table helped correct inaccurate atomic weights that were prevalent at the time. It introduced variations from the strict order of atomic weights. Hydrogen's position in the group of alkali metals contracted its halogen-like qualities. Isotopes were not considered, leading to its inconsistency in the placement of elements like protium, deuterium, and tritium. Some elements were anomalously positioned, such as cobalt atomic mass 58.9 appearing before nickel atomic mass 58.7. These methods laid the groundwork for the modern periodic table, with Mendeleev bringing its most significant contributor. He is often referred to as the father of the modern periodic table, and the modern periodic law is also called Mendeleev's law in his honor. In 1913, English physicist Henry Moseley conducted groundbreaking research on the characteristic X-rays emitted by different metals. He discovered a direct correlation between the square root of the frequency of these X-rays and the atomic number of the elements. Based on his finding, Moseley formulated the modern periodic law, which states the physical and chemical properties of elements are periodic functions of their atomic numbers. Unlike atomic masses, which is influenced by the mass of protons and neutrons in the nucleus, the atomic number solely determines the number of electrons in an atom. Since chemical properties primarily depend on the arrangement of electrons in different energy levels, elements with different electronic configurations exhibit distinct chemical behaviors. Therefore, Moseley argued that the atomic number, not atomic mass as proposed by Mendeleev, should be the basis for classifying elements in the periodic table. The periodic repetition of similar properties among elements grouped by their atomic numbers is known as periodicity. The concept highlights the predictable patterns in the chemical and physical properties of elements as the atomic number increases. The modern periodic table comprises the modern periodic table comprises 18 vertical columns known as groups 1 to 18 and 7 horizontal rows known as periods. Each period and group represent distinct characteristics of the elements. The first period consists of only two elements, hydrogen and helium. The second period includes 8 elements starting from lithium and ending with neon. The third period also contains 8 elements from sodium to argon. The fourth period encompasses 18 elements extending from potassium to krypton. The fifth period also holds 18 elements ranging from rubidium to xenon. The sixth period consists of 32 elements. The seventh is incomplete. Elements in periodic table are classified into 4 blocks based on the electronic configuration: S block, P block, D block and F block. The elements in the first and second row are termed as S block elements with a general electronic configuration of Ns1 and 2. Elements in the group 13 to 18 are known as P block elements having a general electronic configuration Nsn, Ns2, Np1 to 6. The elements from 3rd to 12th group belonging to the D block with a general electronic configuration of N1, D1 to 10 and Ns1 to 2. Lanthanides and actinides placed separately at the bottom of the periodic table are known as F block elements. The general electronic configuration of N2, F1 to 14, N1, D0 to 1, Ns2. This systematic classification helps in understanding the properties and behavior of different elements within the periodic table. Periodic properties and their trends. The periodic properties of elements are closely related to the electronic configuration and exhibit a gradual change as we move down a group or across a period. Key physical properties such as melting points, boiling points, density and enthalpy of fusion and vaporization are influenced by electronic configuration. However, our focus lies primarily on properties like atomic and ionic radii, ionization enthalpy, electron gain enthalpy, and electronegativity. Atomic and ionic radii. Atomic radii. The distance from the nucleus to the outermost electron shell defines atomic radii, which can be covalent, van der Waals, or metallic. Covalent radii. Half the distance between nuclei of adjacent atoms in a single covalent bond. Van der Waals radii. Half the internuclear distance between atoms of neighboring molecules in a solid. Metallic radii. Half the distance between nuclei of adjacent atoms in a metallic crystal. Atomic radii decrease across periods due to increased effective nuclear charge and increased down groups owing to additional electron shells and shielding effect. Ionic radii. The effective distance from nucleus to the electron cloud for ions formed from neutral atoms. Ionic radii follow the same trend as atomic radii, decreasing across periods and increasing down groups. Diagonal relationships in the periodic table occur when elements from the second period share similarities with the elements from the third period group when placed diagonally across each other. Resembles magnesium in group 2 while beryllium in group 2 resembles aluminum in group 13 and so forth. This phenomenon arises due to the comparable attributes such as size, charge to radius ratio and electronegativity. The unique behavior of these elements is attributed to several factors. Firstly, the first member of each group has only 4 valence orbitals available for bonding, whereas the second member of the group has 9 valence orbitals. Consequently, the maximum covalency of the first member is limited to 4, while the subsequent members can expand their valence shell to accommodate more than 4 pairs of electrons. For example, boron can only form compounds like Ba4, whereas aluminum can form complexes like A1, AiF63. Additionally, the first member of p block elements exhibit a greater tendency to form pp multiple bonds with itself and with other second period elements. Example: C double bond O, C double bond N, C triple bond N, N double bond O. Compared to later members of the same groups, the proportionality for multiple bonding contributes to the unique chemical behavior and diagonal relationship with the elements in different period cell groups. Valence electrons are crucial in determining chemical behavior of atoms, as they reside in the outermost shell and are involved in bonding. The valence or valency of an atom corresponds to the number of these electrons for s and p block elements. The valency is typically equal to number of valence electrons. Transition and intertransition elements, however, exhibit variable valencies due to presence of d or f electrons, although common valencies are often 2 and 3. Along a period, the number of valence electrons increases from 1 to 8 as we move from left to right. However, when considering the valency in compounds relative to hydrogen or oxygen, it peaks at 4 before declining to 0. For instance, in Na2O, oxygen brings more electronegativity gains into electrons from each sodium atom, leading to an oxidation state of -2, while sodium loses one electron, resulting in an oxidation state of +1. Within a group, the number of valence electrons remains constant, resulting in elements within the group sharing the same valence. For instance, all alkali metals in group 1 have a valence of 1, while alkaline earth metals in group 2 have a valency of 2. Noble gases in group 18 have zero valence as they are chemically inert and do not form bonds. Reactivity in metals is determined by their ability to lose electrons from their outermost shell. When examining relative trends within a period, moving from left to right across a period, the tendency to lose electrons decreases, leading to a decrease in metal reactivity. For example, the reactivity order for third period elements is N, which is greater than Mg, Mg is greater than aluminium. Within a group, reactivity increases as we move down a group because the tendency to lose electron rises. On the other hand, non-metal reactivity is determined by the tendency to gain electrons and form anions. Within a period, non-metal reactivity increases from left to right across a period, with non-metals tending to form anions during reactions. Within a group, non-metal reactivity decreases as we move down a group because the inclination to accept electron decreases. Regarding oxides, the basic normal oxide formed by the leftmost element is the most basic, while the acidic normal oxide formed by the rightmost element is most acidic. Oxides of elements in the center may be amphoteric or neutral. The inert pair effect refers to the declining tendency of valence shell electrons to participate in bond formation as we move through groups 13 to 16. This leads to lower oxidation states becoming more stable. This effect occurs because the increasing nuclear change overcomes the rise in atomic size as we move down these groups, resulting in s electrons becoming less willing to participate in bond formation, thus stabilizing lower oxidation state. So that's all for today's video. I hope you all enjoyed it. Thank you.